Hi, good morning, everyone. Welcome to this seminar organized by PolyU Academy for Interdisciplinary Research. My name is Qingyan CHEN. I am the director of the PolyU Academy. So as you just see from the video, PolyU Academy for Interdisciplinary Research, or we call PAIR, is a university unit which houses 11 research institutes and 6 research centers engaging in the research related to smart cities, advanced technologies, and also the health and well-being. So today we are very lucky to have a distinguished speaker, Professor Zhongchao Tam, with us. So Professor Tam is a founding chair professor, vice provost, and dean of the academic affairs at the Eastern Institute of Technology, Ningbo, China. So this you probably know that is a new university in China. Is set up by Professor Chen, the former president of SASTEC in Shenzhen. So Professor Chen, priorly moving back to China, he was a faculty member at the University of Waterloo in Canada, where he also served as the founding executive director of Tsinghua Waterloo Joint Research Center for Energy and Environmental Technologies. So Professor Tan's contribution to the chemical engineering and then clean energy has been recognized by the international peers as evidenced by 128 journal articles and 6 technical books. It's a single-authored textbook entitled Air Pollution and Greenhouse Gases, was downloaded by more than 1.7 million times globally. And he is also an elected fellow of the Canadian Academy of Engineering in 2022. So please join me in welcoming Professor Tam. So now floor is yours, Professor Tam.
All right, thank you, Professor Chen. It's really an honor to come to PolyU for this, and thank you very much for the kind words. Okay. Okay, before I start, I'll just explain why the University of Waterloo is on the screen here, because I'm currently working for the Eastern Institute of Technology in Ningbo. It's a brand new university in the making. We plan to open in 2025. But the work I'm presenting here was done in Waterloo, okay, because I moved to China August 1st, just like this is my 3rd month in China. Okay, what I'm presenting is actually what's done in Waterloo here. Okay, so a quick snapshot about the university in the making. We plan to open for business in 2025, growing afterwards, maybe in 10 years, growing to the population of student population about 10,000. We are constantly hiring. Maybe in 2035, we reach a number of 600 professors, like full-time professors, like we call it the PIs. Okay, have 3 faculties focused on STEM, science, engineering, and IT, with social sciences and the business as a supporting maybe faculty, or we call it the college in the United States. This is how the campus will look like in 2027. It's more built on the model, more like MIT style, built along the river of Yongjiang in China. Okay, very long, about 3.5 kilometers long, but very narrow. Okay, it's like a slab there. Okay, but all the buildings look like American. Bit of delay there. Okay, that's how it looks like. The Faculty of Science, Engineering, and Administration buildings. It's very attractive to me. That's one of the reasons I came here. I joined the university. Okay, it looks familiar to me, more like where I was studying in the United States and working in Canada. Okay. Anyway, now to the feature presentation. So the subject is about the water. If you look at the Sustainable Development Goals, one of them is focused on water as well. We currently have about 1 billion people have no access to water. In 2025, it's estimated to reach 1.8 billion. That's a huge number, no doubt about that. So if you look at the industry side, if you are looking at the China side, about 100 billion tons of water is used by industry. And if you look at the power plant alone, I'm interested in power plant because that's where I came from. I was educated in the undergraduate program. I was focused on the power generation. Later on, I worked on the power plant-related emission control, sulfur dioxide, carbon dioxide right now. Now I'm shifting to the water vapor here. So 1 billion tons of water emission from coal-fired power plant alone, that's a huge loss. And it also creates some problem related to air pollution. If you study safety modeling, air dispersion, when air density gets, when air gets heavier, moisture will cause secondary air pollution, okay? Anyway, so that's the main reason. So another source of water is actually in the atmosphere. So a lot of people working on atmospheric water harvesting. This is a very simple concept. Two phases. If it's a vapor, you can use a condensation phase transformation. Then you collect it as a liquid water. Then requires solvent-based harvesting. Another one is a biophysical dew harvesting. And if the water is presenting in terms of fog droplets, it's already liquid, but it's a very fine droplets. So you can use harvesting technology. It's more like a filtration. I'm going to show that right away. Okay. So that's how typical permeable fog collector look like. It's like a screen, just like your fence. Okay, yeah, if you have a backyard, it's the fence for the facility. Okay, but the basic principle is more like a filtration. At least that's how the community consider that, based on filtration mechanism. But you will see after this presentation, it's actually quite different. It's not just filtration. Okay. So you capture the droplets grow by coalescence, and then they depart from the screen and they collect it. So most researchers consider that a failing mechanism called clogging, because the filters will be clogged like a filter for aerosol. So if we compare two types of water sources, one is atmospheric. A lot of research has been done. You can characterize the fog diameter in 1 to 50 micrometers. Don't quote it exactly. That's never 100% accurate in that number. Just a range, okay, about 50 micron or less. But if you characterize the droplets, fog droplets in the cooling tower drift, where you see the big water coming out of this, it's not a stack, okay? It's different from a stack. Stack is the third one. Okay, if you look at the cooling tower drift, it's also in that range below 40 micrometers. So they have some similarity there. If you look at how they travel in the air, of course, there's no speed depending on the wind speed. But in the cooling tower, it's roughly 2 meters per second. And the water content, pretty much there's also an overlap from 0.5 to 5% by weight. And the water content and the temperature range are also close. So that gives me the idea, basically, maybe the technology developed for the atmospheric harvesting can be borrowed, or with some change, slight modification, you can apply the technology for power plant. So that's the motivation for this research. Then we have to start with some literature review, because this, forgot to mention, this is a PhD thesis work, okay, still under development. This is the third year already, okay. So if you look at all the literature in the public domain, most of them are using basically larger than micron millimeter range. The X scale is micron. So basically the 100 means 0.1 millimeter, 1000 is a millimeter. You can see that pretty much in millimeter range. There's no research centered on micron fibers. You would assume as an engineer, I'm not a scientist, I'm an engineer, always care about the money, okay, cost less, do more work fast and with less cost. That's what we prefer. So if you think about this way, if you use a millimeter fiber rather than micron, you're going to save a lot. That's the 1000th scale, right? So maybe we can save some money, material cost. And the spacing arrangement would make the grid more permeable. Air may penetrate through with less energy cost or power consumption. So that's the hypothesis. So we dig further into the literature. We found a lot of publications in the last few years, especially after 2015, hundreds of articles a year. But if you screen each of them in the database, only 7 of them is considered industrial fog, but not a real industrial fog, more like a simulation-based. And 2 conclusions here. One is very little research on industrial-related fog collection. Second, there's no single article published based on the micron fiber. Okay, you may challenge me if you're really in the field. You say, okay, somebody already published the micron nanofiber, electrospinning nanofiber. If you do, you can find that article there. But that's a little bit of misconception here, because that the nanofiber is a membrane. It's not the grid. Okay, it's completely different story there. Okay, filtration based on membrane or permeable grid, that are different stories. Okay, so no research using microfiber for the grid-based work, because when you move air, you want to have a grid rather than a membrane, because one clocks much larger energy consumption. Okay. Anyway, so the conclusion is pretty affirmative. So that motivates us to work on something. Say, can we produce micron fibers? My core research was actually in nanofiber, okay, nano range by electrospinning. I found it's really difficult to make aligned nanofiber, because it's really difficult to make. Later on, we found that you can use near field electrospinning to produce well-aligned nanofiber. That's how it looks like in the, I hope the video works. Okay, that's basically there's a high voltage power supply applied to the needle where there's a syringe coming with all the solvent coming out of it. So then the syringe will print on the plate, which is the programmable. Okay. It looks like a 3D printer, but actually not, okay? The reason is it's not like touching there. The near field electrospinning, if you're in the field, it's not 3D printing, rather it's electrospinning with a random motion. Better controlled, you can see how the solvent works. The beauty of this technology is you can produce patentable structure, like a scaffold for medical application. Okay, so that's one application. But for me, I'm not in that field. Mainly we use it to produce the filters. Okay, well, it could be used for scaffold, actually mainly for scaffold. Okay. And then we produce the sample. We put it under 2 types of microscope. And one is the digital one. You can see how they lay out on the left, lower left. And then another one, we put it under the scanning electron microscope. So to look further, just zoom in to calculate the fiber diameter, which is in the range of 10 to 25 micrometers. It's a narrow range, and we also can control the fiber spacing from 0.05 to 0.5 millimeters. Okay, that's how it looks like when we assemble the test unit, just like a sandwich. Okay, we use a metal support to support it for easy testing, and it's because of the fine, the diameter, it's really look like the spider web, almost the same almost the same like a spider web, but just well patterned, not as beauty as the real spider web. We use the crossing structure. Okay, look like that. It's transparent because of its the thickness. Okay, very looks like that. Okay. And then we we're going to test its performance in the lab environment. Just we generate the fog like using the humidifier, just like the regular humidifier in your house. You can buy one, and then there's a jet shooting against the test unit. That's how it looks like from the other end. Just another view. And you can see the droplets moving around. Some are captured by the unit. As engineering research, we target in two types of environment. One is the open field, like in the atmosphere. The other one is in the cooling tower. It's a confined environment or enclosed environment. So we want to make sure the first two types of environment will have the same or similar impact. Otherwise, we have to do both separately. Otherwise, you're going to have different results. You cannot make the same conclusion. So we tested in open field and enclosure. So the velocity and the profile of the droplets look like that. The velocity, discharging velocity is close to 2 meters per second. And the size distribution is from 1 to 50 micrometers. I would say it's a typical atmospheric fog, and also covers the cooling tower drift size range. We confirm that. And here comes some results. First, we want to make sure, or we want to compare at least before we know it, the enclosure chamber and the open environment, they would have similar results. We measured their performance based on collecting of water, basically millimeter per square centimeter of the unit. Basically, that's a normalized, that's a unit we use to compare. It does show some difference. You can see in the enclosed environment, it helps. It performs better or collect faster than the open environment. And that's understandable because in the enclosed environment, the droplets and the atmospheric disturbance would be minimized. In the open environment, because it's in the lab is an open environment, then air moving around, maybe the incoming profile already changed, right? So, but on the other hand, you can see the difference is less than 5%. That's if you are dealing with the rocket science, that's a huge number. But for engineers, 10% is a small number. So basically 5% is, we are pretty happy with the difference, only 5%. So we consider them as they're difference, but not tolerable. Okay. And then we carry on the research with the enclosed environment. So we take a picture of all the droplets collected on the screen. And then we use image processing, very typical ImageJ software. So we analyze how we call it the water drop now, rather than droplets. Droplets means the fog. Water drop means they already become water collected. We analyze the water drop. We found that something interesting here is just no difference, regardless of the spacing. It's the spacing, basically the gap between the two fingers. This way, or longer, or wider, or narrower. It does not affect the results of the water drop we collected. Okay. Second, the interfiber spacing, the interdrop spacing increases with the fiber spacing. Basically, of course, that makes sense because the drop will attach to the wire or the fiber. So if they separate, the droplets will separate from each other. That's acceptable or no-brainer. However, it does not depend very much on the fiber diameter, but we have to accept the range of the fiber diameter is also not very wide, only from 10 to 20, maybe because not a big difference here. But this is not the main part, just some preliminary test. But something surprising came out is like this. So when we use the microfiber to calculate the collecting efficiency, we use the efficiency rather than the collecting speed. We compared all the results with those literature or as close as possible. We found that our efficiency can reach about 20 and 22.5 somewhere, and the highest in the literature is about 17%. Okay, I would say 25, 17, not a big number to many engineering process. But if you look at this, only one single layer, that thin layer, right? That's still a big increase. Remember, that's only one layer you can see through. It's a very fine, we call it a single, more like a single fiber testing result. Okay, infiltration business, that's a very high efficiency already, because later on you can add layers by layers and then to increase the overall efficiency. Okay, anyway, at least we got this result and I repeated many times. That triggers us to understand, to explore what happened here, why it happens this way. So we did a further study on the fiber spacing and the water collecting related, the x-axis is time, y-axis is the collecting rate, the collecting rate, yeah, per square centimeter, okay. By common, most people would think if you have a two fibers distance this far, the efficiency should be lower than the one because they're clogged, right? They're more area, okay, more solid area. You would hope higher solid area, higher efficiency. But the result tells you it's not the case. Okay, you have a optimum fiber distance. 0.3 in between gives you the highest performance. So that is one, not common sense, not which we call it against the common sense. That's where that's how we just keep moving, moving forward. Okay, another one when we investigate all the original data, we found this one is even more interesting. Most people would think if you have a thicker fiber, it would help you collect more droplets or faster this way because you have a larger solid area, right? But if you look at it, if you compare the results, this one is for one about 10 to 25 micrometers. Not a big difference, as I mentioned in the previous slides. When you use from 10 to 25 micron fibers, compared with those about 100, actually the smaller one or the thinner one collects much faster. You see the result. This is again, and not in line with our common sense. We would think a larger one, thicker one, higher chance for the fog droplet to collect on it, right? So, but that's two phenomena or two findings, which is not, but not in line with our common sense. However, like any research, if you dig further, you're going to find a good reason to explain that. That's what we're going to go after. We try to explain all this. Oh, by the way, I forgot to mention this paper is being reviewed by Chemical Engineering Journal. It's we are revising this, so it's for publication. That's why we did some dimensionless analysis, some widely accepted parameters. We compared this term called shade coefficient. You can see that on the left side is our sample. You can't see the fibers because they're so thin you cannot see them, like a spider web covered by droplets. The shade coefficient is much higher than those reported. In addition to that, we also test the durability and the stability because we make sure this guy is not just like a one shot. So we tested 10 cycles. Each cycle lasts 1 hour. So basically that's a 10-hour period duration. Over 10 hours, you can see the performance. I would say there is another interesting pattern here, but we didn't go after this because we only want just, we're going to do that later. If you look at the performance, it goes up, then down, then up a little bit, fluctuating. But actually, this phenomenon is in line with those published in the literature. Those the top one is by Hong Kong CTU. I was there last night. CTU. Another one, the lower one, is by Lanzhou Jiaotong University in China. So this may be something interesting at the very beginning, but we didn't go very far along that direction. But that does bring us a concern. If you look at some deformation of the structure, it's twisted because of the water dripping, everything, the structure is twisted. If you look at the lower right compared to the one before 10 hours, okay? But no torn, no breaking, okay? So we want to understand what happened, why there are two results or phenomena, just not, it's against our common sense. Let's put it that way. Okay, as an engineer, we want to dig further, see what happened. We analyze the video. This is for 10 micron. This one is for 100 micron. You can see the thinner one, if you compare both. Yeah, it's working. You can see droplets, the fog droplets deposit or collected on the finer ones much faster than the 100 ones. The thicker fiber actually collects the droplets much slower, just by visual observation. And later on, there's a shading, all those things. Okay, that's basically then to give us one more confirmation our data were correct. And the visual observation confirms that. And this is how we analyze it again using the per area collection. You can see that much faster at the micron scale than the 100 micron. You can saw that still micron, but the 100 micron already. Okay, the thicker one collects the droplets slower. Okay. Then we came up with some analysis. Okay. And we further analyze the image. We see from the 25 micron on the top, 100 in the middle, and the 150 and the bottom. You can see the droplets behave differently. For the thinner one, droplets just hanging on there like a dew in the morning, just hanging on the fiber because it's 25. But for the 100 one, it's really surrounding it, because the larger surface area will basically deformed. It deformed, changed. The structure all changed. So we, by analyzing all the video and the data, we just come up with a mechanism. We say maybe for the thinner one, it's easier to deposit. The black one is the fiber size. If you consider this micron, larger one, this is the micron. This is the fog droplets attacking the fiber. These are the upstream coming. If you look at the smaller one, maybe it's easier for the fog droplets to get in touch with the fiber because of the smaller size, comparable size. But when the fiber becomes larger, according to very basic fluid mechanics 101, there is a deviation of the flow direction. Fluid mechanics, if you take fluid mechanics, you will understand that. Because of the change of flow direction and the small size of the droplets, the change of direction may carry away the droplets. That's why at the very beginning, it's difficult for the droplets, for the fog droplets attached to the fiber if the fiber is overly large. Actually, the smaller one, they get along with each other. It's easier to capture the smaller ones. That's what we proposed. And later on, we did some analysis. Later on, you're going to see that. We proposed there is a threshold diameter for the water droplets on the fiber. For example, if the fiber is small, micron, like this, when the droplets collected grow to a certain level, but it's below certain threshold, it still helps collecting because the deviation of the flow pattern is not that significant. Later on, when the droplets keeps growing, this is the threshold. Above the threshold number, it becomes an obstacle for the flow, for the airflow. The airflow will deviate and carry away the fog droplets. So that's based on the experimental data, visual observation, we propose this mechanism. Basically, the larger one, again, as I said, there's always a reason. The reason is the change in the flow pattern. Okay. Then we further examine this. We want to confirm this with a theoretical analysis and later on safety modeling. This is by theoretical analysis. Without going to the detail, you can see the water radius. The y-axis is the efficiency. There is an optimum size for the water radius, for the water drop radius. Okay, as I proposed, like this one. When it reaches a certain level, there's an optimum one, which is the threshold one. So basically, below that size, it helps collecting the fog droplets. Above that one, it becomes an obstacle, deflect the airflow, it reduces the performance. Although it helps, but the effectiveness drops. So that's the conclusion. So come up with a diagram. The y-axis, x-axis is Reynolds number. The y-axis is the dimension is correct size. Without going to the detail, okay. So the next mechanism, we further analyze what happened. What happens when we look at the single large droplets? That's what happens. But it is a group of droplets on the whole screen, not just one, right? Because there's a population there. How they interact with each other, is there another reason? So we explored further. We found the air moves around from the larger droplets. Remember, when you have a larger one here, air going to deviate. Where does the air go? Actually, it goes toward the smaller one. So this was another reason, help improve the efficiency. Because it's a safety modeling, this is another larger droplets. This is small droplets. If you look at how the air behave, basically air carrying the fog droplets, trying to get away from the large water drop, but they got to move somewhere. They move toward the smaller one, because along the smaller one is below the threshold number. Okay, so the safety modeling also analysis shows that. Although there's a deviation, but it's still captured by the smaller drop. So there are two mechanisms to help you grow that. One is from the fiber, the smaller fiber, easier seeding, easier capture before grow to certain size. Second, when they grow to certain size, the airflow deviates or deflects toward the smaller one, continue this performance. So two reasons combined together allowed us to reach record high performance. Basically, that's at least that's what we are proposing. And 4 reviewers didn't object that, which is a minor revision for the other part. Okay, hopefully we're going to get accepted soon. Okay. Anyway, so the greater satellite effect for the, if you compare the micro one in the bottom and the conventional millimeter one at the top, when droplets are collected by the conventional fog, the web, droplets is stuck in the hole or the open area. That's why it's a clogging effect, because there's nowhere for the air to go. Okay, so does not interact with each other. But for these micron ones, the micron fiber is so thin, it's almost negligible. It's like a seed, only a seeding. Then you have the smaller droplets. The droplets play with each other to help enhance the performance. So that's the two mechanisms we hope to propose. And the mechanism behind it is we have a lot of image, a lot of videos to support this, I would say, proposed mechanism or hypothesis. So how does it work? If you have this fiber so thin, the droplets will coalesce and cover this area, and then there's get growth and capture the smaller ones again, keep growing. This is the video. Oh, this is not a video. Okay. So that's how you capture. Infiltration, we stop right here. If it's a filtration of aerosol, okay, captured, we consider it's captured. But this is not a filtration of aerosol particles. This is the collecting of water droplets. When you have so many droplets sitting on the web, you got to let it go down. Then this way you can collect that, become water you can refine it, clean it to use the water, right? To recycle it. When I was talking to an investor in Shanghai, he asked me a question: is your water drinkable? It always ask the question, right? So basically, that's the difference between the thinking between the engineer and the businessman. Okay, engineer care what happens, businessman the final product. Okay, but to reach that goal, you got to collect that water somewhere, then you clean it. Okay, then as an engineer, we study how to clean it. There, one of the expert in the field says, okay, did you test the gravity, how it looks like, all those things? Then we did small research on this. We found there are actually much more than gravity. The shade, we call it the shading in the field. If you look at how it works, there's some numbers. You can see the larger one drop, the shading. But at the end, when it becomes really large, it stays there. That means it's not just gravity. If it's only gravity, then just fall down, keep going like sweeping, right? So it hangs there.
by observation, which means there's something mechanism behind that more than gravity. Of course, if you're an interfacial behavior, you know that wettability, hydrophobicity, those terms, right? We all know that. I'll have another article about that. So to prove that, to convince the reviewer, you can see something coming up there at the corner. Okay, there's water. You see they're moving. The trajectory is not just the vertical, which means there is a coalescence. There's a coalescence effect because of the surface tension and the other mechanism. If you look at the other one, the other shading, if you look at the arrow there, coalescence, but the drop shading due to gravity and coating the water bridge. Okay, basically we're trying to convince the reviewer it's much more than just gravity. Okay, it's not as simple as what we would hope. Okay. Anyway, to conclude, we did a little PhD research work, opening a new field based on for my electrospinning business. Electrospinning, nanofiber, all those things. I started moving into this field to say if we can use electrospinning for environmental engineering. Okay. And looking for a selling point, water is a big deal. So we started looking into this. And fundamentally, we discovered some differences between microfiber and millimeter fiber because they behave differently because of interaction between frog, droplets, and the fiber, and some fluid mechanics behind it. Anyway, that's all my work. Thank you for your attention. Open to any question.
Well, thank you very much, Professor Tam, for your very interesting work. I didn't realize you now also working in this area. You know, in the past, I know that you've been working very hard on the nanoparticles. So now we, yes, open the floor for questions. Yes.
Not in the material side. And it's very interesting work. So my curiosity is, you found any association? Have you found any association between the material of the fiber and the efficiency of the water collection? And then also, what is the association between the temperature of the fiber? Because we know that the temperature is cooler, so I assume the water collection is better. So this two, material and temperature.
Thank you. Both are very good questions. To answer the first one, that is the next step. Theoretically, it definitely affects the performance because if it's a wetting behavior, right? If it's a hydrophobic or hydrophilic, depend on that. If it's a hydrophilic, it helps capture the water droplets maybe, okay? But it may be difficult to shed because it's just hanging there. Right, get heavier and heavier, going to turn the fiber, especially for the microfiber, does not cannot sustain that. Maybe we would prefer some hydrophobic one. So this way, it gets very small, then just keep shading. Okay, depend on the. So it's an interactive parameter. Depend on the fiber size. I already told my student to just go into that area after publishing this article. The second one, temperature, it definitely would affect it because that affects the surface tension, the coalescence, and even the size of this attacking. We call it the challenging aerosol infiltration. Maybe we call it the challenging frog droplets here. So the incoming frog droplets with the size, the performance would depend on the temperature as well. But in Hong Kong, it's pretty humid, a lot of fog, but not, maybe it's a different story, okay? But my research in this part is mainly for the cooling power. In that environment, it's an enclosed environment. The temperature is about 35 to 40 degrees. That's pretty stable. But if you apply for the fog, like in Saudi, in Middle East, in the Africa area, a lot of people working in that field, just to, that may be a factor to consider. That's a great point, yeah. Then that would, you know what, scientifically, yes, you can make a hollow fiber. You can add the coolant in it. But as an engineer, we normally hesitate because that adds to the cost. You see what I mean? If it's a science, if you want to study, for example, in your medical field, right? That's normally not a big concern. But for engineering, especially for the industry or large scale application, I would say theoretically, yes, you can produce a hollow fiber. Hollow fiber, even hollow nanofiber is now doable. That's my research again. You can do it, but the only thing is it's going to cost a lot and the mechanical strength would deteriorate as well, because it's a hollow, not a solid anymore. I would say that's a great idea. You can do some research in that field, see the temperature, but engineering would practice is limited. I would say that. Thank you.
Thank you, Professor Tan, for the interesting presentation. I understand now you as a PhD, I mean, your students' work focus more on the mechanism. In your test, the testing condition, I'm just wondering the testing condition for now you have the capture capacity per unit area of the grid, right? For if you think about the likely application scenario, for example, if you imagine you have a dome around let's say the cooling tower, right? You would be wondering at those actual density and flow conditions. What would be the capture efficiency under that kind of scenario? So I'm just wondering what are the testing conditions in terms of the fog density and also in combination the flow through your grids for the results you show over time about how different or how typical or how different, how close they are to the possible actual application scenarios.
Yeah.
That's my question.
Thank you.
I'm curious about it.
That's a good point. That's a very good point. Okay. First, the condition, we did two types of condition comparison. One is enclosed, one is open to mimic atmospheric condition, open field. And another one is for the drifting tower, which is more confined, stable condition. Okay, so the condition, the size distribution is typical. We did before we do the research, before the student do the research. Okay, read a lot of articles to make sure to ensure the conditions are comparable with those published. The air velocity is about below 1.5 meters per second, somewhere in that range, which is a typical, I would say, stable air condition. And the 2 meters per second is a typical drifting tower condition, so that the velocity we make sure it's the same. We generate the fog droplets using the humidifier, which is a very typical practice by all the researchers. And we confirm the size distribution is from 1 to 0 to 50 micrometers, cover the typical size presented or published for atmosphere and the drifting tower. Okay. That's for the temperature-wise. That may be a little bit different than in the atmosphere because it was done in the lab environment. Okay, in the lab environment, very nice, just like this room, maybe 22 degree, 24 degree, depending on the condition. But in the atmosphere, maybe different temperature there, and wind speed different. And in the cooling tower, maybe much cooler somewhere, but actually hotter. Okay, 35 degrees there, because it's steaming coming out of that. Okay, so the temperature does look different, should be different. And what else in the
density? How about overall fog?
Fog density.
I think that's very important.
Yeah, a fog density. That's a great point. Yeah. So if you have a less fog, right, you're going to have a much lower collecting efficiency. If you have like what we are doing here, right? First, I would say the preliminary test already showed that the lower density, remember we compared the open field and the enclosed environment. The enclosed environment does give you higher efficiency or collecting rate, maybe not the efficiency, sorry, collecting rate. So it does, but that's why this is mainly for certain condition, I would say, the frog density, which is the typical device used by other researchers. We only can compare apple to apple, maybe still in the compared laboratory environment. The method is the concentration. I would say the concentration, yeah, that's a concentration, that's a term. Okay, the concentration would be comparable to those published. But is it the same as in the real environment? That may have to be done by a pilot test or field test. Yeah. I will look into that. That's a good point. Or maybe we can use dilution to change that. Efficiency, I did see the efficiency. Yeah, I think, yeah.
I have another question.
Go ahead.
Okay.
So out of curiosity, the size distribution from the typical cooling tower is called bimodal distribution, right?
That's in the literature.
10 to 20, sorry, 5 to 10, then I think 20 to
Some to
yeah, there is
10, then 20 to 40.
yeah, what is the mechanism there?
Oh,
That's a question.
well, I didn't look into that, but you do see bimodal distribution in aerosol a lot.
Very typical.
Very typical. I think, whenever we try to explain that, mainly because one, for a certain small size, it's diffusion, you cannot control it. Then for larger one, there's a gravitational inertia effect. Somewhere in between is always the valley. Because for a cooling tower, remember, there's also some mechanism to capture the droplets. We call it demister. Just the drift will have demister there as well. You don't want to, it's basically already filtered. Maybe there's some thing related. That's a great point, but I didn't look into that detail. Yeah, that's very interesting. Thank you.
Yeah, we got a number of questions from the internet. Then it's quite a lot. Let me just maybe summarize and then you can answer. Your technology seems interesting, but how do you apply to different type of climate in different nations? Because that might be challenging, right? Then because some are very dry and some are very humid. But well, also when you collect the water for like in Hong Kong, then there will be like a storm water, rainwater, the collection may be more effectively important. But of course, we realize that you use this technology for power plant. So can you comment on different technology for the water collection? And then in terms of your design, is your fiber 25 micron is the best, or what else did you ever consider? Then probably you can also comment on the shape of a mesh. Well,
Okay.
that matters.
Yeah. The shape of a mesh, first I go backward. It was just like it's looking like that, the shape of the mesh, very typical one. We haven't worked on different structure yet, although there are quite different structures already reported in the literature. You could play with it. That's okay. Yeah. The first question was basically in different environment, right? Say in Canada, very cold. In Saudi Arabia, very hot, right? Maybe Hong Kong, very humid. So a different environment. I would say if you play with this for the atmospheric condition, you may have to tailor that for certain condition, for certain weather. This way, more, I would say, engineering design would be needed. You have to do that. So make sure it works for that certain condition, because this only tested for laboratory condition, a very benign condition, right? And the wind, there's no crosswind, all those things, right? So you have to do that, design the product accordingly. But if you want to apply this to the power plant, that's what I'm going after. It shouldn't be a big deal because it's very stable. The power plant is pretty much similar to each other, only difference in the size, the capacity, flow rate, and then maybe some depend on the add-on devices, maybe the concentration or density would change a little bit. You can, with minimal modification, it should be doable, should work. The second question in between was about the what you did, the durability thing.
For example,
25, yeah.
Yeah, 25 micron.
What happens if it's fine? We already presented some. You see the deformation in the grid because the fiber is so thin, it may not be able to sustain its this nice shape. What you're looking at, maybe just twist it a little bit, just like you pull your clothes. Okay, you're gonna have wrinkles on it, right? Over time, okay. Over time, okay. Another concern is the mechanical strength, because you're not going to install it, just test it for 10 hours. You're going to hope for last for 10 years, maybe, right? So that would be a durability issue. I would say 25 micron wood does come with a problem, not as strong as those millimeter one. That's definitely should be the case. I wouldn't doubt that. But you can work on the strength. You can work on the strength, like as another actually just graduated another master student working on enhancing the mechanical strength of nanofibers. Okay, how do you can use different material, cross-linking, all those technology, you can enhance it, because size is not the only factor for strength. Remember, some fiber very rough, very thick, but is not as strong as the fishing string. Right? The fishing string is very fine, but it's still very strong. Okay, very fine, but very strong. So it really depends on the material. You can choose different material, test it, and see. There's a long way to go. There's a long way to go. Did I answer all the questions? Yeah.
Yeah. Okay, we might have one or two more questions from the students here or the young scholars. Yes, over there.
Okay, very inspiring presentation. In your experiment, the flow direction of the air is horizontal, but in the cooling tower, the velocity is vertically. How about the performance in the vertical flow? Will the fibers broken due to there's no other fibers to hold the droplets? Another question is in the vertical flow, there's no droplet sliding down. So will the efficiency become lower?
Okay. Well, that's a great question. Yeah, you're talking about the design. Okay. Normally, it's like a filtration business. You don't want to put your filter horizontally. There's always inclination, angle to avoid those problems that's foreseeable, right? So avoid those problems. And so that's basically partially answer your question. The second one, if it's this inclination, right, like this, what happens? Because we tested vertically, right? But and the air is not horizontal, rather from the bottom. From aerosol technology, you can see that the frog droplets are very fine. Microns at 2 meters per second, it should still follow the airstream. Not a big concern there. Not a big concern, but we could test it. Yeah, maybe some minimal difference. I would expect that. I would expect some minimal difference, but it is a legitimate concern, but we can test it. Then based on my knowledge and experience, I would say if there's some reduction in efficiency, maybe 5% or somewhere, should be in that range, no more than 10%. But meanwhile, because it's inclined, maybe it's easier for the water droplet to fall down for collection part. You see what I'm saying here? Maybe the one at the bottom, but the one at the top, depend on the hydrophility or hydrophilic facility there. Okay. The third one is you're talking about if the droplets stay on the inclined surface, would that just further toward the fiber, right? That part should be actually that should be in the better position because the vertical one would be more. Oh, okay. I forgot to put it in the video. We got a sample here like this in the lab. We put the two nuts, the bolts, metal one, the typical bolts. It's like this. We put it there. That thing, not hit itself, just like a net, become a net. Does not break. So it's a pretty. The fiber itself is already pretty strong. It may change a little bit, but won't tear apart. Put like 2 bolts, just like two bolts finger size with it's much stronger than a spider web, I would say. Okay, it's because of the material we used. Okay, but contact answer your question quantitatively because there's no numbers attached. But that's a great question. Thank you. Any other questions
Oh,
from the
that's a simple question from the internet. What type of anemometers did you use to measure this? Because this is multi-phase flow.
We didn't use anemometer. We use the video, and because that's the moisture there, we didn't measure that. We use the video to analyze that. Follow the droplets.
Okay.
Yeah. Because you have time, you have this thing there. Yeah.
And maybe the last question, the people ask, you have a written book in English as a non-native speaker. So what is the challenge do you have, and do you have any advice to the young people on
It's
how to
a very
write a
good
book?
question. Yeah. You know what? I just not only wrote one English book, I wrote 3 already, okay? And one of them, the latest one, the newest one is how to write in English. If you Google, it's academic writing for engineering publication. It's basically teach students how to write engineering articles and books. Okay, it is a challenge for me, like your age, but when I was a student, and Professor Chen was already a professor in MIT, and but we keep learning. I keep learning, catch up with accumulating the knowledge. Eventually, I discovered engineering writing, not a novel, not some play script. Okay, engineering writing is like an engineering project. You have a certain rules just to follow that one by another. You will get the structure. Okay. If you are interested, I can share with you my book on how to write engineering articles. I always give out to students for free, as long as Springer don't sue me. Thank you.
Okay, well, due to the time limit, I think we have to stop here. Yeah, I'm sorry for those on online. I couldn't really get all the questions posed to Professor Tam, but anyway, I will forward those questions to him. Okay, then thank you again, Professor Tam, for your wonderful talk. For people online, I'd like also to thank you for your participation. So this is the end of the seminar, and we'll announce the next lecture very soon. I hope that you can join us. Thank you.